My name is Steve Boggs. I'm the chair of the physics department here at Berkeley, and I'm really excited that Berkeley can help host the Breakthrough Prize Symposium this year. And of course, I'm very excited for the physicists who won today. So Berkeley had, in addition to, of course, our involvement in Daya Bay with Cambu, Luke, who we're very proud of. Congratulations, Cambu. Berkeley has had substantial involvement in both SNO, which you'll hear about a little bit more today, and in CamLands. So that was Stuart Friedman, who passed away, unfortunately, a couple years ago, but very heavily on our minds today in today's awards presentations. So the discussion this afternoon is on the future of particle experimental physics. And oddly, we had no idea about the selections this year when we chose that subject. So I think we did a good job picking that topic. And so we're going to hear about the full spectrum of particle physics, not just the neutrinos, but they are certainly a critical part of that. So the way that we're going to structure this today, we're going to have 15-minute presentations by 5 different speakers. We'll have time for very brief questions for each speaker afterwards, and then if there's time at the end, we'll bring them up for a panel. So, but we'll have to play that by ear and see how time goes when we get to the end. So our first speaker today is Nima Hyneman, who is coming from the Institute of Advanced Physics. He's a particle theorist, and he won the Breakthrough Prize in 2012. So I think a good person to start off our presentation. So Nima?
Thanks a lot. Well, it's always fantastic to be back here at Berkeley. And our topic today is the future of particle physics. So what I want to, I'll be talking about motivations for great big circular colliders, maybe 100-kilometer scale colliders that can operate as Higgs factories in a first run as E plus E minus machines and 100 TeV proton-proton colliders after that. But since the topic is the future of particle physics, I want to spend, because it's very important for the subject, I want to spend a few minutes talking about why there is a future for particle physics, okay? Because it's not a completely obvious question. People say, look, before the LHC, we had a very good expectation that we would see something like the Higgs, a new particle, or Higgs or something like it. And now when we go beyond, we don't know where the next milepost is. We don't know for sure whether the next colliders are going to discover new particles. So how can we possibly justify continuing? It's a very important question, and we have to confront it head on if we're going to talk about the subject. And I think part of the misconception about this, how do I go forward here? Oops, this doesn't, do I have to do that? What do I click to make this thing move forward? Huh?
The right one, I think.
Right, okay. So part of the misconception is what particle physics is actually about. And one of the sort of popular pictures for what it is that it's a study of the basic building blocks of matter. That's one aspect of it, but it's not the most interesting aspect of it. The most interesting aspect of it, it's not merely the study of the building blocks of matter. We study these elementary particles ultimately because we care about what they tell us about the fundamental laws of nature. And what we discovered in the early part of the 20th century is that the story of the fundamental laws is most effectively told by studying the interactions of the elementary particles at the highest possible energies. And they're governed by the still mysterious union of the ideas of space-time and quantum mechanics, the 2 big revolutions of the early part of the 20th century that we understand well enough to construct this fantastic edifice of the standard model of particle physics, but which leaves us with many really fundamental paradoxes left as we go to the 21st century. So saying this all again, is it true that new physics means new particles? If our definition of new physics is that we have to guarantee before going to the next frontier that we're going to discover new particles, we should quit right now, because we can't guarantee that. That's the honest statement. But new physics does not mean new particles. We care about new particles because they're a stand-in for something more important. We care about new phenomenon and new principles. That's what we really care about. And from that point of view, we're actually in an incredibly interesting, almost unprecedented situation in the history of our development of in the development of our subject. That can be sort of summarized by this slogan. A big summary of what we learned in the early part of in the 20th century is whatever the underlying laws of physics are, compatibility with the pictures of space-time and quantum mechanics guarantees that at long enough distances, we'll have elementary particles. The physics will be described by elementary particles interacting in the simplest possible way, with 3 particles coming together at points in space-time, and that the elementary particles have to be picked from a menu of spins of particles that have spins 0, 1/2, 1, 3/2, and 2. That's something that can be determined almost from pure thought once you know these basic principles of relativity and quantum mechanics. And that's something we knew on theoretical grounds, and the story of the Higgs is essentially part of the completion of this story. We discovered the Higgs on July 4th, 2012. That turned that red 0 into a black 0. We finally saw an elementary particle of spin 0. It plays a crucial role in allowing us to connect the physics of massive particles at very long distances to massless particles at very short distances where their interactions are so incredibly constrained by these general principles. And that's what's so important about the Higgs. It's the first really new elementary particle we've seen. We've never seen an elementary particle of spin 0 before. And its existence is tied up with all sorts of other mysteries. On the one hand, if we posit that it exists, the kinematics of how to describe it are well controlled by our understanding of relativity and quantum mechanics. But on the other hand, from many points of view, it's very mysterious that it should exist at all. Here is a famous one. If we look at something as simple as the energy in the vacuum of the universe, we add up the half h bar omega for all the harmonic oscillators for the particle of Box modes for every particle in the universe. It has contributions which are enormous, sensitive to very high energy scales. The leading contribution is the energy density of the vacuum. That should curl up the universe by all rights to a size of 10 to the minus 33 centimeters, and it hasn't. That's the cosmological constant problem. But there's a sub-leading piece to that, which has to do with the dependence of the mass of the elementary particles on the Higgs. That should give the Higgs an enormous mass, 32 orders of magnitude bigger, or 16 orders of magnitude bigger as a mass than we've observed. And these are both associated. This is the cosmological constant problem. This is the hierarchy problem. And it affects the Higgs in that subleading term precisely because the Higgs is a particle of spin 0 that has the opportunity to have a mode that fills the entire universe. Here's another aspect of it which more clearly illustrates why spin 0 is a problem. We understand why a particle like the photon is massless because of a discontinuous difference between the number of degrees of freedom of massless and massive particles with spin. Okay, a massless particle with spin has 2 degrees of freedom, a massive has 3, and so there's no way that interactions with virtual particles in the vacuum can discontinuously convert a massless spin 1 particle to a massive one. Not true for spin 0 particles that have exactly the same number of degrees of freedom for massive and massless. We have no good understanding why the interaction with the virtual particles in the vacuum don't give the Higgs an enormous mass. So it's the first really new elementary particle we've seen. And in this sense, it's really new physics. It's a new phenomenon. We've never seen anything like it before, and you don't discover something new that you've never seen before, especially one that's tied up with the drama about quantum fluctuations in the vacuum and just walk away from it. Okay? So it's really new physics. We've never seen anything like it. Many people think it's a harbinger of some profound new principles at work in the quantum vacuum, and so experimentally, we just have to look at it closely. So there's very obvious questions associated with it. We've never seen a point-like scalar. The picture of the Higgs that we get from the LHCs, it looks roughly elementary. In other words, its size is a little bit smaller than its natural Compton wavelength. Okay? But not so much smaller. And there's a very natural question. How point-like is it? That's something for experiment to answer. That's a question that today we know the LHC will not answer. Okay? It won't do so much better than it's done already. Just to drive this point home, what we know with LHC resolution today, and what we're likely to know through the final run of the LHC, is that the Higgs could be about as elementary as a pion. A pion was a spin 0 particle, and it's also relatively light compared to its Compton wavelength. Okay? So it has a size which is smaller, about 5 times smaller than its actual Compton wavelength. Its size is set by, for example, the mass of the rho meson. Well, that's about the picture of the LHC that we're going to get. That's about the picture of the Higgs that we're going to get from the LHC. So it's possible that even though it looks like it's an elementary spin 0 particle, and there aren't a lot of other friends around, that it's about as elementary as the pion. It would be great to know if the Higgs is composite. It would be great to know if the Higgs is something like a pion. But its implications, whether it is or isn't, are gigantic, right? I mean, if it is, it's another layer of the onion. It's very important. We'll have to understand it. If it isn't, it's much more theoretically dramatic, right? Then we really are in completely uncharted territory of a sort that we haven't seen before. We have to decide this question, not theoretically, but experimentally. Okay, there's lots of theories that make the Higgs something like a pion, but we'd like to know experimentally whether that's possible. Okay? So in order to do that, we just have to study it. Okay? So we have to, instead of having the fuzzy picture, this is the picture of the Higgs that we'll get from a Higgs factory. Okay? By looking at how the Higgs interacts with other particles, almost literally like looking at it, instead of with photons bouncing off of it, you see how a Higgs decays to couples to 2Z particles. Okay? That's going to give us a picture that looks much, much more like this. Okay? It'll increase the resolution compared to what we get from the LHC by a factor of 10 or 20 or 30. And that's what's needed. For example, if we do this at a Higgs factory, we'll know for sure whether the Higgs is like a pion or not. Okay? And if it is like a pion, there'll be deviations in the strength of its interactions compared to that of a point-like picture. And if not, not. But we'll know definitively the answer to that very important question. Here's a quick plot just to give you an idea of the leap in precision that you can get at a Higgs factory versus what you can expect from the LHC. And I won't have time to go through it in detail, but across the board it's a factor of 10 or 20. And in some of the most important coupling constants, namely the coupling of the Higgs to 2Z particles, it's almost a factor of 30 better than you can do with the LHC. It's fortuitous that the one that you do the best with at this machine is the one that has the deepest theoretical significance and is the cleanest measure of whether the Higgs is composite or not. All right, now there's one more important question associated with whether the Higgs is point-like or not, which is the following. Does the Higgs look point-like to itself? Okay? It might look point-like to other things and yet not look point-like to itself. In fact, the self-interaction of an elementary particle is perhaps the most basic process we can talk about in quantum field theory. And yet no elementary particle other than the Higgs can experience it. Okay? We think that gluons can interact with each other, W's interact with each other, but they always change a quantum number. They change a color or flavor or some quantum number. The only particle that even has a chance to interact with itself is an elementary spin zero particle. So you have to go look, does it interact with itself? It's a brand new kind of interaction we've never seen in nature before, the most basic, simple possible one. And the LHC is not going to be able to tell us even whether this interaction exists, never mind measure it. Okay? That's what you need. For that, you need to make hundreds of millions, billions of Higgs particles, enough so that this process happens at a sufficiently high rate that you can actually see it and measure it. And that's ultimately, that's the actual rock-solid physics case. That's one of many things that going to 100 TeV proton-proton collider will do, produce enough Higgs particles in order to be able to actually see that process and perhaps measure it to the 5% level, 5 to 10% people. People are fighting right now about whether it's 5% or 15%. My bet is that eventually it'll settle down closer to 5% or even better as people start being more imaginative with how they go about doing this. Okay, so it goes from not knowing whether this interaction exists at all to being able to actually see it. All right, so those are the most basic questions about the Higgs, this new object. We have a very fuzzy picture of it from the LHC. We're bound to continue to have a relatively fuzzy picture of it from the LHC, and that's what these facilities are going to allow us to do. Of course, a 100 TeV collider does something else. It blasts into the energy frontier, and that's something that we've been doing for 100 years or 50 years, depending on how you count. And so there's absolutely no reason to stop doing it now. If 100 TeV seems crazy, I'll just remind you that it's only 2 times more powerful than the superconducting supercollider, which is something we are going to do 30 years ago. Okay? So it's pathetic if the human race cannot, 50 years after we first started doing about it, go a factor of 2 compared to what we could do back then. This is not crazy technology. It's not, it's not la-di-da thinking. This is something that we can do, and there's absolutely no reason we shouldn't keep doing it. But by going to these higher energies, we will have power to produce new particles at 10 times, roughly 10 times the reach of the LHC in mass, more like 5. Okay? 5 to 10 times the reach of the LHC in mass. And importantly, the probe of the quantum fluctuations in the vacuum scales like the square of the energy of the machine. So it gives us a probe of those quantum fluctuations with a power 100 times larger than the LHC. Okay, so there are various ways, if you want to speak more professionally about very concrete physics questions that these machines are going to tell us something quite robust about. If you ask the question, for a long time we wondered what breaks electroweak symmetry, and now we know the answer. It's the Higgs particle, the Higgs field getting an expectation value breaks electroweak symmetry. The next obvious question from there is how is electroweak symmetry restored as you go to much higher energies, or as you go to much higher temperatures in the early universe? Okay? So that question about the nature of the phase transition to restore electroweak symmetry is something that we'd like to explore experimentally. And anything which affects the nature of this phase transition is bound to give you percent level deviations in the couplings of the Higgs, as well as new particles that are accessible to the 100 TeV collider. There are questions involving why the Higgs particle was like to begin with, the infamous or famous, depending on how you think about it, question of naturalness. This is something that was a huge motivation for the construction of the LHC. We haven't seen any of the particles that were suggested by these arguments yet. Okay? It's not obvious that that means they're not there. There's something a little bit wrong with the way we're thinking about it. There's something a lot wrong with the way we're thinking about it. We just don't know. The only way we can decide is to go and look. I want to point out something that David Gross keeps emphasizing whenever we talk about these things, that never in history has it been true that to understand physics at an energy scale E, it suffices to go to the energy scale E. You go to 10E. You go to 10E so that things aren't confused and you're not in transition regions and you really get a picture of what's going on. That's really what happened with QCD. The characteristic scale of QCD is 300 MeV. And if we're stuck at 300 MeV doing experiments there's no way in hell we would figure out that there's quarks and gluons underneath the whole thing. That needed just to go to 2 or 3 GeV in order to see that picture emerge. Okay? And finally, the idea that dark matter might be weakly interacting particles. And the very simplest picture for what dark matter could be, their mass is something that's not accessible to the LHC. It's just tough. The simplest pictures of dark matter have these particles weigh 1 TeV or 3 TeV. They cannot be produced at the LHC, but they will be produced in a 100 TeV proton-proton collider. All right, so there are some technical things that I don't have time to go into, but let me just finish by making the most obvious remark that here we're talking about the long-term 2 or 3 decade future of particle physics, but right now we're probably entering or in the most exciting phase of the running of the LHC. And almost all of us in this field are spending most of our waking moments worrying and thinking about it and being excited about it. But I want to emphasize that no matter what we see at the LHC, the fact that we haven't seen anything already tells us that we have a solid argument for proceeding and making plans for this next generation of accelerators. And that's both in the pessimistic and the optimistic cases. The pessimistic case where we see nothing but the Higgs, then we're humbled as theorists, certainly, many of us, okay? We need to study this particle experimentally. We have a fuzzy picture from the LHC, so we have to go and look at it. Let's say we do see new particles. Euphoria, hallelujah, right? Well, let's say we see some colored particle that weighs 1.5 TeV. I can guarantee you 500 theorists will call it the superpartner of the top quark. The problem is it will not produce enough of them at the LHC to be able to verify that it even couples to the Higgs. Never mind that it does the job that it's supposed to do in more detail to solve the hierarchy problem. See, this is not a trivial statement. Rah, 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 keep going no matter what. Had we discovered 300 GeV gluinos in the first run of the LHC, we'd be swimming in these particles by now, and then it's with millions of them. Then it's not so obvious that this is the next thing you want to do. But now it is, because even if we do see them, we're going to make 1,000 of them or 10,000 of them, enough to actually produce them and claim a discovery, but not enough to be able to tell us a story about what's actually going on. And for this, you need actually a Higgs factory, which can confirm that these things couple to the Higgs, as well as ultimately going to 100 TeV to actually have that factory and study them in detail. All right, so something particle physicists love to see is pictures of the planet with big rings on them, okay? And I think one of the most exciting things that's happened in the past couple of years is that these pictures with big rings on them are being drawn. They're being drawn by our friends at CERN, who are imagining an 80-kilometer tunnel going underneath Lake Geneva. That'll be this next big step beyond the LHC. And by Yifeng and his friends in China that are drawing maps of 50-kilometer and 100-kilometer rings on the ground 300 kilometers northeast of Beijing. Okay? I think this is amazingly exciting, amazingly important, and worth putting a lot of effort into supporting both things in order to try to make sure that these machines actually go from being a dream to a reality on the necessary decades timescale. And there's the final question of the cost that always comes up. I've stolen the slide from Yifeng. The cost of these machines is 10 billion in your favorite units. Okay, so and there's no sugarcoating it. That's how much they cost. But Yifeng has pointed out a number of times that the fractional costs of these projects compared to GDP of any country at any point in the last 30 years has always been roughly the same. Roughly 10 to the minus 4. Okay? So the SSC, when it was canceled, was 10 to the minus 4 US GDP. The running cost of the LHC now is around 3 10 to the minus 4 European GDP. The cost of these projects in China is of the same order. Okay? This is something human beings have done before. By the way, Tycho Brahe's boss, the king of Denmark, spent 8% of his GDP to give him an island, okay? And this was a really good idea because people remember this guy, except I just didn't, sorry. But people remember this guy. This is something human beings do, right? There's very few things of importance that we can do on this planet before we shuffle off this mortal coil. And this is one of them, okay? This is one of them. Am I putting you on the spot, Yuri? You know that? All right. So let me just end by saying that certainly, and not just my view, the scientific issues that we're facing today are amongst the most difficult and profound ones that fundamental physics has faced since the 1930s. It's fascinating to me that the questions that have been raised by the biggest experimental discoveries of the past 2 decades, the discovery of the accelerating universe and the Higgs discovery, they both go to the heart of something we don't understand about the combination of these ideas that were handed down to us from the first part of the 20th century. There's something we don't understand about the nature of space-time, quantum mechanics, and the vacuum. And both of these big discoveries are pointing to something that we don't understand there. In the case of the accelerating universe, our friends in astronomy have no difficulty making the intellectual case that we have to keep going, we have to measure W, we have to really know that it's a cosmological constant. All the more power to them. I support you 100%. Okay? We have a similar case that we could be making in particle physics, and we have tons of measurements we can make. There's a big, rich experimental program revolving around the Higgs avatar of these same problems. And I believe that these future circular machines are the way to go about doing them. So the scale of our vision and ambition have to be commensurate with what the science demands, and we should be more, not less aggressive in pursuing it. Thank you very much.
To keep on schedule, let's see if we have one burning question for Nima before we, and we'll have time for a panel at the end, hopefully.
What is the case linear versus circular?
Oh, the linear collider does some measurements that are quite similar to the measurements you can do about the Higgs circular machine.
Sorry, you need the
there are
microphone.
some measurements that are absolutely complementary. Okay, so for example, the Higgs factory is a little bit better at measuring the couplings of the Higgs particle to the Z. Not much. The linear collider allows you to measure couplings of the Higgs particle to top quarks, which is something very important that at least the sort of simplest versions of a circular Higgs factory don't allow you to do. So the physics case is a complementary. But I should also say, just sociologically and geopolitically, nothing would make it easier for the rest of the world to build a circular machine. Or perhaps I shouldn't speak for China, but I imagine nothing would help motivate more China building a circular machine than Japan building a linear collider. Okay, and I think this idea that we've gotten used to, that everything has got to be international kumbaya and we all have to get along and get behind one project. There's some truth to it, but competition is a good thing too. And it used to be 50 years ago that every country wanted to have its own big collider as a matter of national prestige and as a matter of developing talent and so on. And that's something there's some truth for that as well. So, well, as I said, you can. Yeah, in this context, you can get, so let's say nothing existed other than a linear collider, then we'll learn very similar things about how point-like the Higgs looks to other particles, and we'll learn something about the way the Higgs interacts with the top quark, which is very important. And we won't get, except maybe very asymptotically, if the thing runs for a long, long time, we won't get a picture of how point-like the Higgs looks to itself. And of course, we also don't get access to the energy frontier. So that's what's exciting about the circular machines, is you get to have your precision cake and eat the energy frontier too, okay?
Thank you, Nima. Okay, we have a, yeah, let's thank Nima again. We have a slight order change from the printed program. So next up is Viata Hyneman. She's a professor of experimental particle physics here at Berkeley, and she is also the deputy director for the ATLAS project on the Large Hadronic Collider. So we get to, up here it is, Viata. So Viata's going to talk to us from the experimentalist viewpoint on the collider physics. So thanks, Viata.
All right, thank you. Yeah, so I will now talk about the second LHC run, which Nima already alluded to. The best way of illustrating that we're now in a new phase at the LHC is this display of an event. This is a high mass dijet event, which actually has a mass of 8.8 tera electron volts, which is 10% higher than the energy we had in run 1. So this is experimental proof that we're now beyond the first LHC run. All right, so this, you know, so the LHC accelerator here in the Geneva area, and now in run 2, the energy is now 13 tera electron volts, nearly 50% higher than the first LHC run. The heart of the LHC are these LHC dipole magnets. So this shows a cross-section of them, one beam going one way around, one the other way around, and what is seen here is the complex magnetic field. The magnetic field, in order to keep these protons on the circular ring, they have to hold a field of 8.3 Tesla, and there's 1,200 of these. In order to hold this very large field, they need to be able to hold currents of 12 kiloamps. And this is done by using superconducting wires. You see here an example of a superconducting wire used in the LHC ring, and here you see how much this would be in copper. So that's completely impossible to construct magnets like that. However, the reason that we actually were limited in the LHC in the first run is because the connections between those magnets were not able to hold such high current. So we could only go approximately to half the LHC energy. And in the past 2 years, the interconnects between all these magnets were refurbished to ensure that they can actually hold the full current, so we can go to the full field and thereby to an energy of 13 to 14 tera electron volts. This shows pictures here of the ATLAS and CMS experiments, these very giant detectors. Here the ATLAS experiment with the two people over here, and here CMS, which is heavier than the Eiffel Tower. And this, I can't resist to show some of the pictures of these gorgeous experiments here. Now we also, so using these detectors and the LHC during run 1, we took a lot of data. This shows the data taking from that time. We took data here at energies of 7 and 8 TeV and proton-proton collisions with a total luminosity of 25 inverse femtobarns. And then the LHC also collides lead ions, either with each other or with protons. And in total, we took about 4 billion events each year, which corresponds to 5 petabytes of raw data. Using this, we made a lot of measurements. In total, the ATLAS experiment alone has published 484 papers to date, based on these 3 years of data taking, measuring basically, half of these publications are basically measurements of standard model processes, while the other half are searches for new physics. It's a very vigorous program of searching for new particles. This shows a summary of many of these measurements, which shows cross-sections for the production of many particles. So this is just inclusive proton-proton interactions. These are W and Z bosons, TT bar, top quarks, etc. And in all cases, you see the data here compared to the theoretical expectation. And all of these, the data agree actually with the expectation. One thing you can also see here is the Higgs, so where we've launched a measurement program, and we've actually got several measurements now in this already since the discovery. Now, just to give you an idea what really the experimental challenge is if you just imagine the most frequent process that any proton interaction occurs at all happens at the same rate as a pneumatic drill, then these measurements, these processes like W and Z production, they happen as often as like the Super Bowl. So they're like once a year. So this is what we have to dig out of all this pneumatic drill. And if you go to other processes like TT bar production or even raw rare, these happen like once a century. Okay? So that's really the experimental challenge, to dig out these processes out of all the frequent ones that we are not that interested in. Okay, so then of course during run one, the big highlight was really the breakthrough from run one was the discovery of the Higgs boson, and I can't resist to show you here pictures corresponding to this. Here the Higgs in the diphoton decay mode, this little peak here, and here the Higgs in the 4-lepton decay mode, which Nima already discussed. And this was celebrated in 2013 with the Special Fundamental Physics Breakthrough Prize. You see here the prize winners on the podium. All right, so what do we now do from going from run one to run two? So as I said, what was limiting us during run one was the ability to go to these high currents in the magnet to go to an energy of 13 TeV. So all of these interconnects were actually refurbished and replaced so that we're now able to go to this higher energy. And at the same time, several other improvements were made so that we can now also increase the rate of collisions per second from 20 million to 40 million. All of this together relates to the fact that, and we're running, basically the run is just started this year and is going until the end of 2018. So just as an example, so the Higgs boson, in run one, we had approximately 50 events where the Higgs decayed to ZZ via 4 leptons, and in run two, we have more than 700. So that allows us to enter the precision study phase rather than just the observation phase. Just to give you an idea, I don't want to go through this, but just to give you an idea, there's this humongous amount of work that was done. This is really incredible engineering here. For instance, here 10,000 splices were consolidated with 27,000 shunts, etc. So this was a huge amount of work. And we also, at the same time, we also improved the detectors themselves. So for instance, one thing we did is we have a silicon pixel detector very close to the interaction point, which in Atlas used to consist of 3 layers, and we've inserted a new layer, and this was largely developed here in Berkeley, actually, at only 3.5 centimeters. So this is the very first layer that any particle that gets produced in the Atlas experiment sees, and by going closer to this, before it was at 5 centimeters, we can better resolve whether the particle actually originated from the interaction point or maybe from a displaced particle decay. Okay, and so then what was very exciting for us was on June 3rd when we had the very first 13 TeV collisions in the experiment. In the beginning, we were a bit skeptical, looking at the monitors, is everything working, etc. But then there was a lot of happiness when we actually saw the first collisions appear on the screen like that. And we indeed even saw and this is very close to the experimentalist chart, we even saw our little 4th pixel layer producing hits right away in the first collisions. So everything is working very well. The experiments are functioning. So what can we learn in terms of physics now from run one versus run two? What I'm showing you here is the relative ratio of the rate of processes as a function of the mass of the system that gets produced. So the protons interact with each other and produce a system X. For any proton-proton interaction, by going to this higher energy, we're not increasing very much. It's only an increase of about 10%. However, as we go to higher and higher masses, this increase becomes larger and larger. So for Ws, which have a mass of 80, it's about a factor of 2, as you can see here. For top quarks, which we produce in pair, it's approximately a factor of 4. But then for more exotic particles, supersymmetric particles like gluinos, which could have a mass of about 1.5 TeV, the increase is much, much bigger, like a factor of 50. Okay? So there we would have only produced 1 a month. This is not enough to discover it because there's also some background. Now in run 2, we would produce 50 a month. So, so we've taken data throughout the year. So this is here in beginning of June. This is when we started. And you can see that in the beginning, we were not actually increasing the data set very much until end of August. But since then, we've taken a lot of data. So this data set is not yet as large as we had in run 1. It's about a fifth as large as that. But it is more powerful because of the higher energy. So in terms of its power, in some cases, it's already much more powerful than run 1. And we've recorded 1.7 billion events. I'll show you now some results which we have produced during the summer using approximately 2% of the total data of this year. So for instance, we measured the rate of this total proton-proton interaction cross-section, that proton-proton going just to anything. And indeed, we see here, so this shows this rate as a function of center of mass energy. There's many experiments have made these measurements since the 60s. And here, this is now the new measurement here, this blue point. And indeed, we see approximately a 10% increase with respect to what we saw before, as we expect. We also measured the rate of W bosons, where indeed we see this factor of 2 increase we were expecting. And also for TT bar anti-top production, we see approximate factor 3.5 increase. So you see here the energy of 8 TeV, which we had before. Now at 13 TeV, we've already made 3 measurements that agree with the, and they indeed agree with the expectation. Now, as Nima already said, one of the really important things that we want to do in the second LHC run, and even in the third and the fourth one, is to understand the Higgs boson in much more detail. So, for instance, the theory predicts exactly how the Higgs boson couples to standard model particles. It depends on the mass and on the type. And with theory, we can calculate exactly how the Higgs boson gets produced. There's several ways of producing it when these can be predicted with a good uncertainty. In particular, these can be predicted with an uncertainty up to 3%, this one more like 10%. And also our theory tells us exactly how often a Higgs boson decays into which particle, depending on it. So 58% into B quarks, 22% into Ws, et cetera, et cetera. So by measuring the Higgs boson in all its production modes and in its decay modes, we can constrain how the Higgs boson couples to the standard model particles. And this is our first, this is the summary of what we've done in run 1. At the moment, we have quite sizable uncertainties, something between 10 and 40%, or for some cases like the muon, we haven't actually seen that conclusively yet that it couples at all and have just a very large uncertainty. So in run 2, we should be able to improve the precision by how well we can test this by a factor between 2 and 3. Another thing we can try to understand is, for instance, whether the Higgs boson has anomalous decays to other new particles, for instance, to dark matter. So if it could be that the Higgs gets produced in association with a Z boson and then it decays to dark matter particles. So we've looked at that in run 1 already. We're looking by looking for a Z boson recoiling against nothing. And we see the data here compared to the hatched histogram is what we would see if there was some sizable production of this. And we already have learned that the fraction is less than 15% of all Higgs bosons decay in such an invisible way, but we should be able to test this in the future to 5% or so. And this is quite interesting. You will see later a talk by Tom Schatt about dark matter constraints. This is complementary to trying to observe dark matter directly in underground experiments by looking, so this is mostly working in the low mass region. It only works if the dark matter mass particle is less than half the Higgs boson mass, which is why it cuts off here. Something else we can do, as Nima already alluded to, is also find supersymmetric particles. We did not see them in run 1, despite trying really hard, with about 100 papers published by Atlas alone on supersymmetry searches. So what we're looking for is, for instance, one of the most interesting processes where you have gluinos being pair-produced, and these then decay, and we see, again, these chi-1 zeros. These are potential dark matter candidates and many quarks, which manifest themselves as jets. So we see multiple jets and something escaping, basically momentum balance not working. And so this is something we look for. And for currently the run 1 limits are, so we already know that these particles must have a mass bigger than about 1.3 TeV. between 1 and 1.3, depending on how they decay in detail. And in the future, we will be able to test the 1 TeV more. So basically, we're doubling the mass reach for such particles. One particularly important particle related directly to the hierarchy problem is the supersymmetric partner of the top quark, the stop. And here, so this orange area is what we're excluding right now, up to about 650 GeV, depending again on the mass of the neutralino, the dark matter candidate. And we will extend this significantly by also more than a factor of 2 in the future. We have already started actually looking for new physics. So even this, so as I showed you, we only have so far analyzed 2% of the 13 TeV collisions, just because most of them were only coming in the past 2 months, and we're really actively working on analyzing these now. So I can't show you the results yet because the analyses are not ready. But some we've already, with 75 inverse picobarns, already we were able to push beyond what we were able to do in run 1. So one thing we can look for is black holes, which evaporate immediately via Hawking radiation, and we look just at the total energy in the event. Black holes you would see at very high energy values here, but you see the data here consistent with the background expectation only, so no black holes yet. All right, so let me conclude that the LHC is exploring this very interesting fundamental scale of nature, the weak scale, and that this scale is full of mysteries, which Nima already discussed in much more detail. And the second LHC has started. We're taking data. Our experiments are working very well. We took approximately 1/5 of the run 1 luminosity, and we're analyzing this right now. And it's very, very exciting. So I would say, so initially the topic was to see whether there are any breakthroughs within the next 5 years. So run 2 is running in the next 4 years, so it's certainly possible. And then, for instance, Fabiola, who's now the director, would smile very happily, and maybe we can celebrate another breakthrough.
Okay, so we're going to move on to our next speaker, who is Lawrence Hall. So we're moving back to theory. We're going to hear about dark matter. So Lawrence Hall is a particle theorist here at UC Berkeley, and he's the former director of the Berkeley Center for Theoretical Physics. And he will jump right in as soon as he gets his microphone on. So. Thanks, Lawrence.
So it's a real pleasure to talk at this breakthrough symposium. And it was a difficult task thinking about what to talk about, because they stressed we should think about what could the next breakthrough in the next 5 years be. And I thought about it, and then I thought, yeah, I want to speak after the LHC talk, because that's where I think we're going to have a breakthrough in the next 5 years. Oops. Well, so much for the breakthroughs. Okay. New searches for dark matter in particle collisions. I'm going to predict a very, very definite idea for what we might discover at the LHC. What we might discover is not just a new particle, but a new particle whose decay is going to tell us what the origin of dark matter was and how it was produced in the early universe. That's a pretty definite prediction, and in order to understand and for you to evaluate that prediction, you need to know where we are in what I call the cycle, the discovery cycle. It's not always true, but it's often true that discoveries in physics go through a cycle where it starts with asking questions, basic curiosity, framing how to get experimental set up to get your data. Once you've got the data, you look at the data, you look for patterns, and patterns emerge, and if you're lucky, a real theory comes out of that. And then and then on to the next cycle. So it often, but not always, but it often goes in these cycles. A critical question then is, what is the time scale for this cycle? And that depends on the sort of phenomenon that you're interested in. If you're in some very, very restricted phenomenon, it could happen pretty quickly. But if you're interested in the really big stuff, the really big cycles, you know, the time scale can be a century. It's not nice to say that, but it's true. And so I thought it would be fun to look at a half century of particle physics in the era of 27 to 77, roughly. The dates are a bit fuzzy. But the questions appeared right at the late 20s here, when we needed to understand what was the description of particles in their interactions such that they could be consistent with the recently discovered quantum mechanics and also special relativity. That was the driving thing one had to do, and it took a 50-year cycle to get there. The data poured in the 30s, 40s, 50s, 60s, every decade, all the way up to the 70s. The data was really pouring in, starting with neutrons, muons, began with particular particles, but ended with symmetries and interactions. Along the way, there were plenty of patterns emerged. Here's a pattern from the early 60s of the kaons and pions forming this hexagonal structure. It's pretty obvious there's a pattern behind there, and that pattern was what led people to introduce quarks as the constituents of all of hadrons. Theory was much harder. The first part of the theory came in the late 40s, the quantum version of electromagnetism. Here there's an electron interacting with a photon, and it was a real struggle. The 30s and the early 40s were a real struggle, and the struggle continued in the 50s and 60s, and the real theory didn't emerge until the 70s, the theory of the strong interactions and the electroweak unification. So this is the sort of pattern, and it can take half a century or so, but the key point to take away from this is that by the late 70s, there was a theory of particle physics, and it's immensely important to actually the difference between having a theory and not having a theory. So from the late 70s, we have a theory. Here's the standard model. The theory you can think of as a bunch of particles, the up, down, and electron, the familiar ones of ordinary matter, but there's 3 generations. There's a pattern for you right there that we don't understand. In fact, I don't understand the pattern of these symbols, but I have to construct my own theory for that, I think. But anyway, these particles are going along as they're traveling. They interact with these force fields. That's the photon, the Z, the W. These are the particles of the standard model, the gluons, and finally the Higgs boson of just a few years ago. And the interactions are parameterized. If you go deep down into this vertex, there's a whole bunch of quantum numbers and symmetries and 18 free parameters that have to be obtained from data. But this is what we call the standard model. The electroweak unification part of it was finally deemed to be correct in '77, and it only took 2 years for these gentlemen to win the Nobel Prize. Precisely that year, one of them, Glashow, a very bold fellow, decided that he would make predictions about the future of particle physics. And he says, "We live in interesting times. We have a theory at last of strong, weak, and electromagnetic interactions. Many new accelerators are building to test our theory. So let me tell you a little bit about the predictions that he made back then in 1979. The first predictions had to do with the matter and the force fields, and this hasn't come out at all, which is a real shame, so I'll have to just tell you about what's supposed to be in here. This was the late 20th century version of what happened to the Mendeleev Table in the 1860s. He came up with a Mendeleev Table, and you had to discover the elements that fit in the blanks. And here, the blanks were the top quark here, and here the blanks were the W and the Z, and here the blanks are the Higgs boson. In a sense, one might say this was no big deal making these predictions, because once you knew the theory, they pretty much had to be there. That was true for the W and the Z, wasn't quite true for the Higgs, could have been something else, but you get the picture. And in fact, these particles, of course, the discovery took ages, but they came. But next we come to a bolder statement, and this is very bold given the exclamation marks and was proton decay. So what this should be is the proton decaying to a positron and a pi zero. And he made it. He made this prediction for very, very good reasons. And the experimentalists ran out and looked for it, and they've pushed the limit on the lifetime by 6 orders of magnitude, and so far, no success. So even though what looked like the best prediction for the next era, the next cycle, the beyond the standard model cycle, even the best predictions go awry. And that's what we have to expect once we're swimming without the real theory anymore. So what can we do with our theory? The good news is we can calculate stuff in particle collisions. The reasons why early on I thought that they discovered the Higgs boson even before they were willing to say they discovered it was we can compute how many events they should get, and it worked out right. So it was just very, very plausible that the discovery was there. The bad news is that we can't compute what the universe contains. And if we had a real theory, we should. We should be able to compute what the universe contains. Well, we can get the photons right. That's the big success. But when it comes to electrons and protons, we're really, really way off. We've got theories, but we just can't do it. Worse, we don't know what most of matter in the universe is. The so-called dark matter makes up most of the matter in the universe. And whatever we think about it, we know that it's not a particle of the standard model. So here are my predictions. My prediction is that the next breakthrough in particle physics will be in data. It will not be in patterns and theory. Because even though this beyond the standard model cycle has been going for nearly 40 years now, I don't think we're at the level of being to extract the next level of theory. I think we need this continual cycle of more and more data. We've had some hints. We've had dark energy. We've had neutrinos, and they're fantastic. We need more. Okay? So that's the first thing. The second thing is that I'm going to guess that the next breakthrough will tell us something about this dark matter. That I'm much, much less sure about. And this I'm going to say is that I don't think it's going to be our favorite candidate of dark matter. I think it'll be some huge, big surprise. What probabilities do I ascribe to this? Yeah, well, I really think it's going to come from data. Is it going to be dark matter? I really don't have a clue, but I think it will be. If it's dark matter, is it going to be some non-standard theory? Yeah, I think probably so. But I'm going to go further and say that in the next 5 years, there's a very specific new long-lived particle that will be discovered at the LHC, and that its decays in the will tell us exactly how the dark matter was made in the early universe. I really don't dare to predict the probability that this is right. Okay, so the early universe. So the early universe is a hot gas. We've got particles colliding. All the red dots here are standard model particles. Everything's in thermal equilibrium at some high temperature T. The great thing about thermal equilibrium is that it erases initial conditions, and you can hope to do a calculation at somewhat low temperatures. What is the dark matter? What is the reaction that determines the dark matter abundance? These are the key questions that we need to answer. And I'm going to talk about two very general mechanisms. One's called freeze-out, and probably the majority of the people in the audience know all about it, but I'm going to go through it anyway because I want to contrast it with freeze-in, which you probably don't know so much about. Freeze-out, we've had a 30-year job of trying to find direct detection of a freeze-out particle, and maybe it will. That's also a great possibility for the next 5 years, but I'm going to go for this freeze-in candidate. Okay, so freeze-out. At high temperatures, the standard model and dark particles are scattering off each other. They're in thermal equilibrium. Below the temperature of the dark matter mass, the dark matter particles in blue annihilate away, and the dark matter abundance is determined by this cross-section. Here's a cartoon of how it goes. I'm going to give you some time sequences or temperature sequences. Here's the dark matter and the standard model particles in thermal equilibrium. On the vertical axis here is the ratio of the number of dark matter particles to the number of standard model particles. And on the horizontal axis is temperature, and we're at very high temperature. And at very high temperature, these are comparable number densities. Now, as the universe evolves, the first thing that happens is that as it's expanding, the numbers just dilute. The ratio of the number density of dark to standard stays constant. Notice the temperature's dropping. But as the temperature drops down towards the dark matter mass, we're not quite there yet, but we're nearly there. Now we go to temperatures below the dark matter mass, and the number of dark matter particles starts to precipitously drop because of this annihilation process. At some point, the dark matter particles, the blue particles, are so dilute they can't find each other, and at that point, we say you freeze out, and you get a freeze-out relic abundance. And the great thing about this is that we can compute the relic abundance in terms of that annihilation cross-section, and Viata showed a plot very similar to this one. Here's the cross-section as a function of the mass of the dark matter particle, and the direct detection searches where a galactic dark matter particle scatters off a standard model particle are these curves here, and here's some CMS searches, these horizontal ones from LHC. So let me go on to freeze-in. Freeze-in is exactly the opposite of what I've described for freeze-out. In freeze-in, the dark matter particles interact with standard model particles only very, very weakly. At high temperature, there was no dark matter particles around. There was just no dark matter at all because there's been no time for them to be produced by collisions of standard model particles. However, occasionally dark matter particles are produced, and they're produced because there's two new particles. Not only is there a dark matter particle, but there's a mother particle that I call M. And the dark matter particle comes from the decay of a mother particle. There could be hundreds of models for this, the same as there are 100 models for freeze-out, but I want to give you the generic mechanism. So the dark matter abundance is determined by the lifetime, that's what this weird thing means, of this mother particle decaying. So let's go through a similar sequence of temperature slides to show how the dark matter appears. At very high temperatures, we're starting off at very, very high temperatures, there is no dark matter particle. There's no blue particles there. There's mother particles and there's standard model particles. But as the universe evolves and the temperature drops, a few mother particles decay, and they make the dark matter particles here and here, and you see that the number density of dark matter particles is growing. It's growing in towards equilibrium. Here we go. There's dilution, but we're getting a relatively more and more dark matter particles until eventually the production of them stops. And the reason it stops is that the mother particles have all annihilated away and there's no more mother particles to decay to them. So this is a totally different generic mechanism for making dark matter in the early universe. Here's freeze out and freeze in compared as a function of temperature. The freeze out, you start with a huge abundance and it drops off. The freeze in, you start with none, and it comes in and levels off. Okay, we can't understand any of that, so we better not talk about it. So the key question is, can we measure this at the LHC? Can we actually make a mother particle and watch it decay to dark plus standard at the LHC? And if so, could we measure enough in order to be able to reconstruct what happened in the early universe? So here we make a mother particle at the LHC. It goes out through the detector. Maybe it stops in the hadron calorimeter. Maybe it lives a second. Maybe it lives a month. But eventually, it decays. We can't see the dark matter particle coming out here, but we can see the standard model stuff coming out here. The possibility of long-lived stop particles has been searched for. And the exciting thing is that there are limits from CMS and from ATLAS that show that you can put limits on stop particles over 12 orders of magnitude in lifetime. So you've really got a very, very powerful probe for looking for long-lived new massive particles at the LHC. It's not just stop particles. It could be that the particles, instead of going all the way out here before they decay, it could be that they decay much, much more earlier on. I don't know what happened here. But they decay much earlier on and give you leptons or jets. Or they may decay right close to the interaction vertex, and you may get what are called displaced vertices. But each of these three detection mechanisms gives a lifetime or a distance, the distance lifetime between less than a centimeter all the way up to kilometers. And we can test, we can experimentally test these lifetimes. So everything that's colored here, we can actually see. So what is the prediction from freeze-in? Here's the key slide, and I've only got, I think, another one after this. Here's the key slide, which gives you the prediction for, let's suppose the mother particle weighs 300 JeV, so we can make it at LHC. Then this red curve here gives you the predicted lifetime as a function of the dark matter mass in order that it gives you the right dark matter abundance. Okay? And you can see that if the mass is a few keV, the lifetime is short, and we'll see it as a displaced vertex. If the mass of the dark matter particle is 100 GeV, it lives longer, and we'll see it as a stopped particle that lives about a month or so in the detector before it decays. But we can see all of that, okay? In this formula, which is totally unreadable, tells you how to relate how these quantities are related. But the key thing is that if you can measure the lifetime of the mother particle, the mass of the mother particle, and the missing mass, the dark matter particle, then you can compute how much dark matter there should be in the universe. And if it comes out right, you've resolved the puzzle of the origin of dark matter purely by looking at LHC physics. So I started off talking about the half century from quantum mechanics to the standard model, and what a great half century it was. We're now into the next cycle, the beyond the standard model cycle. We're about 40 years into it. I think that we're still at the level of framing the questions, thinking about the puzzles, and looking for new data that is going to guide us. That's not to say that we haven't made progress in theory. Of course we've made progress in theory. We've got many, many ideas over these decades that are really a tremendous progress. But we don't know how it all fits together. We don't know which theory is right. We may not even have anywhere near the right theory. So the questions. Here's some of the questions. Quantum theory of gravity. Why is the standard model what it is? What's the origin of mass hierarchies? What's the origin of the small numbers? Well, I've placed my bets on the contents of the universe. I think the next breakthrough is going to be, we're going to be able to figure out what the contents of the universe is. Thanks very much.
Well, I'm sure that raised lots of questions, which we don't have time for. So we'll go back to that. Thanks, Lawrence. So our next speaker is Tom Schutt. He's an experimental particle physicist from the Stanford Linear Accelerator and Stanford. And he's going to give us an experimentalist view of direct dark matter detection.
Actually, this is, I think this is a nice, enjoyable contrast, the back and forth between the theorists and the experimentalists. I want to talk about looking for the everyone's favorite type of dark matter that Lawrence no longer believes is what we're going to, or maybe never believes, is what we're going to is what we're going to find. Well, the thing I wanted to say is that from an experimental perspective, the story I'm about to tell is compelling enough that a large number of people have spent, well, in my case anyway, almost my entire career looking for this stuff. And so I want to back up a little bit and sort of give my naive view of why it's compelling. In fact, back way up to gravity. So where's the laser? Top. There we go. Newton actually, when he first talked about gravity in orbits, he sort of had this idea that if you throw a ball, it goes a distance. If you throw it harder, it goes further. But gravity is trying to bend it. And so the balance between it wanting to go straight, so-called centrifugal force, if you will, and gravity results in a point where you throw it just hard enough and you get an orbit. And that orbit is a balance between gravity and the tendency of the rock to go straight. If we come to the solar system, his prediction, which is that the velocity of something is falling off if you get further away from the sun, and there are the planets. And then the measurement matches theory, just Newtonian gravity, just beautifully. And in fact, in some sense, if you measure this curve, when you measure this curve, you've weighed the sun, because the sun is providing the force that's holding all the planets together. And one of the main points here I want to make is that Newton was right, that gravity has now been tested to from sub-millimeter scales to the size of the solar system, billions of miles. That's a vast spatial range for which one simple theory works beautifully. So then the thing is, why don't we go to the next scale up? And that's a galaxy, 100 billion stars, looks like a whirlpool, it's rotating. Everything is orbiting around its own sort of mutual gravity. And does gravity work there? Well, we think probably gravity works, but something certainly doesn't. This is a galaxy. It's rotating, and here's, just like in my last graph, here's the velocity, the distance out from the center, and here's the velocity of things. And you predict something like this curve here if these objects on the periphery are behaving just like the solar system. The mass of the stars that are present is what's driving the rotation. And in fact, the data famously doesn't agree. This has been measured now for some huge number of galaxies, and so there's some other form of matter, we think. I guess in principle it could be that gravity is wrong, but there's lots of reasons we don't think that's the case. My laser is fully run out. Oh, there it is. And so galaxies are full of some other form of matter, which we say is dark. And in fact, it's not simply galaxies. If in another talk, and in fact in another whole session not titled Particle Physics, we could go on about the evidence from bigger scales than galaxies and cosmology and the microwave background. The fact is that dark matter permeates our understanding of the universe back to the earliest days of the Big Bang. And so, for instance, this is a view of the Milky Way. The Milky Way would be a galaxy, and it's embedded in this sort of larger, sort of diffuse component of mass, which is overall about 10 times as much mass, maybe 7 times as much mass as in the stars and the dust out of normal things. Part of that story, which I didn't tell, it really is very obvious from cosmology that the dark matter is not made of any normal elements. It is not made of neutrons and protons or anything built up out of neutrons and protons. So then it's natural to look to particle physics. And indeed, this is the particle physicist view of the world. This is like the particle physicist equivalent of the periodic table. There's these fundamental particles. They all have different masses, and there's a few known forces. In this set of particles, only these ones here are stable. We know we can create all these. They live a short time. None of these work out to be the dark matter. But let's think about that a little bit. How could we have the dominant form of mass in the Milky Way not be normal matter, and we've never detected it? And that gets to what we mean by the size of a particle. Here, for instance, is an electron, and it's got an electric force field, but then at a very small scale, it's got a weak force field. And the ratio of these forces is 100,000 and 100,000-fold that this force is shorter range than the electric force. A neutron, for instance, has a strong force, which is about 100,000th the size of the electric force, and also a weak force. And then there's the neutrino, which we know about. It only has this tiny little weak force field, which gives it an incredibly small size. So if a neutrino comes at ordinary matter, it passes right through, unless it just happens to strike, in some sense, the center. So in this picture, what would make sense as the dark matter? For something to be all through the galaxy and not have been seen so far, it's natural to make it something that has effectively a very small size, or perhaps indeed a force field that is either like or is the weak force we know about in particle physics. Then there's the freeze-out argument, which I decided I didn't have time to explain, and so very helpfully Lawrence has explained it to you. Let me phrase it my way. Any stable, exotic new form of matter in the plasma of the hot big bang, and what do I mean by that? I mean, if there's a particle physics at a higher scale that we don't yet know, which would have created matter that was interacting in the early universe, if that particle happened to be about the weak scale of particle physics in terms of its size, then it would be dark matter today. And this is the compelling argument. Some years ago, people called it the freeze-out argument. Some people now call it the WIMP miracle. I think it's better to call it the freeze-out argument. That makes people look for a certain type of particle. You give it a weak force like a neutrino, but a mass, say, about like a gold atom. So it's a WIMP, a weakly interacting massive particle. And this is still a very compelling idea, and we ought to go test it. How would you test it? Well, here again is a galaxy sort of shown in cutaway with a, perversely in white, the dark matter in a halo. And all the matter in this halo is orbiting just like the rotation of the Milky Way. And so we know the speed of these particles. If here's a detector that's, say, about a meter in dimension, 100 billion of these particles will go through it, given the velocity and density of these particles that we know from astrophysics. Or that's about 10 to the 16th a year. An interesting thing about a neutrino is so small. How small is it? A neutrino is so small that if you wanted to stop it, you would essentially need a light year of lead. You go to the dentist and you get a lead shield for an X-ray, and that's maybe a 32nd of an inch thick. If you want to stop a neutrino, you need a light year. A light year is about 10 to the 16th meters. So if you combine the idea that there's 10 to the 16th per year through a meter-like thing, and they have a probability sort of an inverse of 10 to the 16th meters, then in a meter dimension detector, you might get about 1 per year. And that's the experimental goal. We want to build a detector. I'll explain the detector in a moment. And we're going to see about once a year one of these particles hitting it. The problem with that is that radioactivity is about 100 billion times higher than that. So it is like looking for the proverbial needle in a haystack. We have to remove ambient radioactivity from just uranium and thorium and potassium around us to an extreme level in order to look for these interactions. One piece of radioactivity, of what you would think of as generally as radioactivity, is high energy particles from outer space, cosmic rays. These are high energy protons in particular and other particles raining down on the atmosphere, creating a cascade and a shower of particles on the surface of the Earth. One particular piece of that is a muon, and to get away from muons, you have to go deep underground. There's a set of labs around the world. One in particular is in South Dakota in a gold mine, that is a tank of water in which there is a detector, and being a mile underground, there's very few of these cosmic rays striking it. So now inside of that water tank, we have a detector. I would like to point, there we go. This is like the cartoon I just showed you, and a dark matter particle could strike it, say it's coming from below. But the problem, of course, I mentioned is the radioactivity. This particular detector is from the Lux experiment. And the problem with the radioactivity is that outside in the rock, you had all these gamma rays and neutrons, and they were trying to penetrate. This enclosure we're in is a water tank. We fill it with water, and that water will sort of stop all these particles. Water is not a particularly great material for that, but it's cheap, and you can put a lot of it. Even people are radioactive at this scale, so this fellow has to get out of the water tank before we fill it, or he'll be radioactive for the experiment. Let's look a little bit at how the detector works. There's actually a large number of groups worldwide with different detector ideas as to how to do this. But I'm going to talk about one particular one just to illustrate how this works. So this is a so-called time projection chamber where the particle comes in, strikes material in the middle here. And the material in this case is liquefied xenon or liquefied argon, and leaves. And there's a flash of light from the site where an atom or nucleus of an atom was struck hard by the WIMP. You measure the light with light sensors, photomultiplier tubes, and also electrons are drifted upwards. There's meshes here that create a strong electric field, and you pull the electrons to the surface of the liquid, and you actually pull them out of the liquid and in the gas. They make a small discharge, like at the center of a neon lamp, and you get a localization there. And so you basically can see where the event was in this direction from where that light is, and the time difference between that flash and that flash based on the electron drift speed gives you the depth. And so you find out that there was an interaction in this detector, and you know exactly where it was. That's the so-called time projection part of this. Here's what the data actually looks like from the Lux experiment. The first flash of light can be as small as 2 measured photons. This is a photon, and that's a photon. This is time. And then a little while later, the electrons get to the surface, and you get a much bigger flash, and that's measuring the electrons. Now, if we want to have a detector, and there's 100 billion times too much radioactivity, and then we think we've seen dark matter, how are we ever going to prove that we've seen it? And the way we will, in this standard WIMP paradigm of dark matter, is that the dark matter is fundamentally a little bit different than almost all backgrounds. Dark matter strikes a nucleus, whereas most backgrounds are from things that strike an electron. A gamma ray strikes an electron in an atom. And so here's a low energy electron getting struck by a gamma ray, and in blue is where the electron wandered around and made charge and light that gave you signal. This is a scale that we cannot possibly resolve in a meter scale detector. That's about the width of a human hair, 1/10 of a micron. That'd be a small human hair. But if I think of a little box there and I expand it out, now we're looking at something that's about the size of 100 atoms. That is the recoil track if a particle, which a WIMP will, strikes a nucleus, and you get a very small track. These are about the same energy, very, very different sized track, both on a microscopic scale. The density of this track compared to that track leads to a different signature in the amount of charge and light in this class of detector. So here on the vertical scale, is a measure of how much charge to how much light. And on the horizontal scale is a measure essentially of energy, the light signal alone. And we expose the detector to an intense amount of what will naturally be the radioactive backgrounds. And each dot is an event where the detector was struck. And we populate a region here kind of between these blue bands with a little spillover. And if we turn around and expose the detector to a neutron source, we populate a region between these red bands. Neutrons also look like WIMPs on an event-per-event basis, but neutrons are quite a bit easier to get rid of and to recognize otherwise in your detector. And here's the world's leading data set looking for WIMP dark matter. Some population of events between the blue bands I showed you, and in this red region, a little spillover from the blue region, but nothing centered on the red region. So unfortunately, to cut to the chase, we haven't seen the dark matter yet. But this is a very promising way to look for it. This was essentially 100 kilograms of material in a fraction of a year, and we've seen nothing. There is a very competitive set of experiments looking for this type of dark matter. One particular one, which myself and a number of people actually in the room are part of, was the LUX experiment, and now a next generation LUX Zeppelin. So just to give a sense of where things are headed, this detector is, instead of made of 300 kilograms of xenon, it's made with 10 tons of liquefied xenon. This is now 1.5 meters scale. The previous one was only 0.5 meter in scale. It'll be the largest dark matter experiment and 300 times more sensitive than LUX. This is the way we present our results. This is sort of a map of our knowledge or ignorance of dark matter. We don't know the exact cross-section of dark matter, essentially the size of it. We have guidance from the freeze-out argument. The freeze-out argument picked something sort of very vaguely, well, on this plot. Perhaps not so much at the bottom of the plot and not so much at the very top of the plot, but vaguely on this plot. For various reasons, if you think it's a weakly interacting particle, you would expect it to be related to the mass scale, which gives us the weak interaction, and that's more or less on the horizontal axis of this plot. If you sort of throw that out, then we can start going down low or very, very high. When you make a measurement, let's pick this one here. This was the measurement about a decade after this whole idea came up. And the very first of the sort of the modern detectors, they made a line like this, and what that meant is anything above this was ruled out. So a bigger cross-section would have meant more interactions, and that's excluded. And this line just goes straight on off. If the dark matter particles are heavier, there's fewer of them, and that's why this line curves up. 100 GeV here is sort of like a heavy atom. This is the current LUX experiment, so this is the world's exclusion now. We know it's not here. These are various models from Supersymmetry that are still allowed after the LHC runs. And this is where LZ is going. I'm on my last slide. This is interesting. Since the field started, when actually limits were about here at this -5 level, we've advanced a good 4 orders of magnitude, which is really impressive. When the idea first came out, I think of Lorenz's cycles, we had detectors that had a fraction of a kilogram and no background, and we set limits. Now we're building detectors that are on the 100 kilogram scale, and we haven't seen anything. We now basically see how to plow right on down. Give us money, and we're going to go. For better or worse, something has now come up. In the last several years, people thought hard about where this was headed and realized that there are neutrinos from cosmic rays which are producing signals which look very much like the WIMP dark matter. Unless we can build a detector which can actually measure the direction of those individual tracks, this will be a floor which we cannot go below. This will be a practical, within money bounds, limit to what we can do, and we're getting close to it. So one thing we should definitely do is measure as much of this region as we can down to this neutrino floor. There is no upper end of the data here. Down at lower masses, that's yet a whole other idea, and the different type of technology can push in that direction. Although that's sort of the next world. So what is my summary? My summary is that we know there is dark matter, and we don't know what it is. Weakly interacting fundamental particles are a good guess. They are a guess. But they're a good guess from both cosmology and particle physics. They certainly have been a good enough guess to launch a whole industry of people trying to do this. And after much effort, I'd say 20 years of effort, we do know how to test this idea to the limit it can be done based on this neutrino background. And we should do that. And if we're lucky, the dark matter will be there.
Going to tell us
Thank you.
more about what the award was given in this year, neutrino physics.
Thank you. It's a great honor to be asked to speak here. So you've all heard of the God particle. I'm going to talk about a particle at the other end of the spectrum, perhaps the lightest fundamental particle there is, but one that could shed light on how we come to be here. So the neutrino is a fundamental particle so tiny that it was originally thought to be massless. They come in 3 flavors, and those flavors are defined by the charged leptons with which they interact: the electron, the muon, and the tau. And they interact incredibly weakly, so much so that they're actually very hard to detect. To illustrate that, the Sudbury Neutrino Observatory detected neutrinos produced in the sun, and one of the things they sought to see was a difference between the flux during the daytime, when the neutrinos have just traveled through the vacuum, and during the night, when the neutrinos have also had to cross the entire span of the Earth. And astonishingly, they saw no difference. So you can put the entire Earth in the way of a neutrino, and it will just pass straight through. Another property of these particles that makes them very intriguing to study was first seen by 2 state-of-the-art experiments, pun intended. One of these was Superconducting, which detected atmospheric neutrinos produced from the decay of muons in the atmosphere. That decay produces both muon neutrinos and electron neutrinos in a ratio that we can predict. However, Super-K detected these neutrinos coming from all directions, both from above, from the sides, and from below. And what they saw was that when looking at the muon neutrinos from below, there seemed to be a deficit. So that's the neutrinos that have had to travel the longest baseline. They seemed to be disappearing. The second experiment is the Sudbury Neutrino Observatory, or SNO. SNO, as I mentioned, detected neutrinos from the sun. These neutrinos are produced in the electron state. Now, a number of experiments prior to SNO had looked for solar neutrinos and seen a significantly reduced flux compared to what we expected from solar models. What made SNO unique was the use of heavy water as a target, which allowed a measurement of the pure electron neutrino flux, which was suppressed in agreement with previous experiments, and the total flux of neutrinos independently of flavor. And that flux was in agreement with solar model predictions, which confirmed our understanding of the sun and told us that, in fact, the neutrinos produced in the sun in the electron state were changing flavor before we detected them on the Earth. Of course, we now know that this is due to neutrino oscillation, which is the idea that although neutrinos are produced and detected in their weak or flavor eigenstates, they actually propagate in their physical or mass states. And physicists being as creative as we are, those are just called 1, 2, and 3. So this idea is entirely analogous to classical coupled oscillators. So if you picture 2 pendula on a string, if you set one of them swinging, as you watch over time, the other one will pick up the motion. And the idea here is because energy can be transferred through the coupling by the string. So this is just like a neutrino starting in the electron state, oscillating to the muon state, and back again. However, if you took these 2 pendula and you set them moving in what's called a normal mode, in this case, if you offset them by the same amount and set them swinging, they'll stay in that state, and that's analogous to the neutrino mass states. So in a simplified 2-flavor picture, you can view this as basically a rotation of your basis. So the electron neutrino is a large part nu1, but it has a small component of nu2. And if you view that graphically, you can picture the nu1 and nu2 states as your pure states, and then the electron and muon neutrino are a composite of those. And so if you create a neutrino in the electron state, it's some fraction nu1 and some fraction nu2. Those then propagate at different speeds, and if you detect it sometime later, it's a different combination, giving you some probability that you detect it as a different flavor. We can actually evaluate that probability. It's shown here. And you can see it depends on the energy of the neutrino, on the baseline, the length that that neutrino has propagated, so that explains the results seen by super K. And it also depends on this term delta M squared. This is the difference of the squared neutrino masses. So it's this term that tells us neutrinos have to have mass in order for neutrino oscillation to occur. So the observation of neutrino oscillation is what told us at least one of the neutrino states must have a non-zero mass. And this is really a fascinating process because this is entirely a quantum mechanical effect, and we're observing it on macroscopic scales, on distances of hundreds of kilometers. So there were then a number of terrestrial experiments which really confirmed that the observed flavor change was due to neutrino oscillation. One of these was the Camland reactor experiment, which looked for electron antineutrinos produced as a byproduct of nuclear fission in reactors. This experiment was actually led by Stuart Friedman in the US, who passed away a few years ago. It's a great shame he can't be here to celebrate with us today. Camland had a beautiful result, which you can see here. They actually saw the L/E dependence of the neutrino flavor change, which was really the definitive sign that this is due to oscillation. More recently, the JiaBin experiment has also looked for reactor neutrino disappearance, but on a much shorter baseline, which makes them sensitive to a different set of oscillation parameters. And then there's the long baseline experiments, K to K, T to K, MINOS also, which look for neutrinos produced in accelerators. You can produce a very high energy beam of neutrinos, and these experiments saw muon neutrino disappearance, and T to K has actually now seen the first sign of electron neutrino appearance. So we now have a very complete picture of neutrino oscillation, and you might ask, why are we still studying them? What more is there to learn? Well, the weak nature of their interactions actually allows us to use neutrinos to probe places we otherwise couldn't see, from the center of the Earth to the core of the sun to far distant supernovae. They're also a fascinating particle in their own right. We know that the nu2 state, the second mass state, is heavier than nu1. That comes from solar neutrino measurements. But we actually don't know whether the nu3 state is the heaviest or the lightest of the three. So that gives us two options for the ordering of the neutrino mass states, or the mass hierarchy. We also don't know the absolute neutrino mass scale. We don't know how far offset from zero these masses are. But perhaps the most interesting property of the neutrinos is that they have the potential to be their own antiparticle. And neutrinos are actually unique among the known fundamental fermions in having this property. And if this is true, they're what is called Majorana particles. And it's this potential property of neutrinos that, at least for me, is somewhat reminiscent of some of M.C. Escher's work, particularly the tessellations, where the negative space is basically creating the same pattern, moving in the opposite direction. So this property of neutrinos could actually go so far as to explain the origin of our matter-dominated universe. That's a fairly grandiose statement, so that needs some explanation. So let's talk a little about matter and antimatter. To a large extent, the interactions that we know about conserve the difference between matter and antimatter. And what I mean by that is they're created and destroyed in equal amounts. So we would expect the same thing to be true of the Big Bang. And the universe should contain equal amounts matter and antimatter. In order for there to be any asymmetry, we need to observe something called CP violation. CP violation is basically a measure of the difference in the behavior of matter and antimatter. So if neutrinos exhibit CP violation, then the probability that a muon neutrino can oscillate to an electron neutrino would be different from that same probability for the antiparticles. Now, if we look at the universe, we do see that it is out of balance. It is clearly a matter-dominated universe with very small pockets of antimatter. And that is actually very fortunate for us, because we know what happens when matter and antimatter come together. They annihilate. So if the universe was made up of equal amounts of the two, we would not be standing here discussing this today. So we need to explain this asymmetry. And to do it, we need a large amount of CP violation. Some degree of CP violation has been observed in the quark sector, but it's not sufficient to explain the degree of asymmetry. So how does this connect? Well, if neutrinos are Majorana in nature, then they can undergo something called the seesaw mechanism, which in effect splits the neutrino into two particles. There's the very light neutrino, with which we're familiar, that we've detected and even created on the Earth. And then there's a much heavier sister particle, so heavy that we have not yet detected it, but it could have been created in the Big Bang. And if this particle exhibits CP violation in its decays, then that could explain the current matter-antimatter asymmetry. So in order to explain that asymmetry, we need two things: Majorana neutrinos and CP violation. So how might one look for Majorana neutrinos? Well, for a very small number of isotopes in nature, for which beta decay is energetically forbidden, they can decay by a process called double beta decay, where essentially two neutrons undergo beta decay simultaneously, and you get a pair of electrons and a pair of neutrinos. But if neutrinos are their own antiparticle, they can effectively annihilate inside the nucleus, and the only thing that escapes is the electron pair. Now, the predicted half-life for this process, or the current experimental constraints, I should say, are incredibly long, 10 to the 25 years. For scale, the life of the universe is 10 to the 10. Fortunately, Avogadro's number is very large. So if you have about 100 moles of one of these isotopes, you do actually have some chance of seeing this process. And if we observe it, if we see this neutrinoless double beta decay process, that shows that lepton number can be violated. It tells us that neutrinos must be Majorana in nature. And as a bonus, it actually gives us a measure of the neutrino mass, because the rate of the process depends on that mass. So this is really a very exciting field, and there's been an explosion of technology in the experiments looking for this process. And the reason is actually similar to what we were just hearing about dark matter. It's because this is a very rare process, and you expect a tiny number of events in your detector. So you need a very clean detector. You need to reduce radioactive backgrounds. You need to be very deep underground to reduce cosmogenics. You need good energy resolution. You need a very large target mass, because it's such a rare process. And basically, all of these different technologies have different pros and cons. They each have several advantages in the required features. So it ranges from ultra-pure germanium detectors to bolometric experiments, time projection chambers, and even very large-scale liquid scintillator detectors. Now, if we look at the sensitivity of these experiments, we tend to show it on this figure. It's called the lobster plot. You can sort of see the lobster claws coming out. This is the lightest neutrino mass, and this is the effective Majorana neutrino mass. If we look at current limits, they're sitting at around the sort of 150 to 400 milli-electron volt scale. And if we look at what we might achieve in the next 5 years, there's a number of experiments coming online, and they will significantly improve the sensitivity. So we'll be able to push down to masses as low as about 50 milli-electron volts. So there's a good chance there may be a discovery in the next 5 years. And then, of course, if there isn't, the question is how one improves sensitivity beyond that. So that's the search for Majorana neutrinos, but then we also need CP violation. This is a much longer timescale project. It's more like a sort of 15 to 20-year scale, but I want to mention it just to complete the picture. This is an experiment called the Deep Underground Neutrino Experiment, or DUNE. And the idea here is to create a high-energy beam of neutrinos at Fermilab in Illinois and send them 800 miles through the Earth to a deep underground detector in the Sanford Research Facility in South Dakota. And this beam will be able to produce both neutrinos and antineutrinos, allowing a very high-precision search for any difference in the behavior of the two. So in my last couple of minutes, I just want to discuss some new technology that may potentially herald the breakthroughs of the future. And this is a new target medium that has been developed called water-based liquid scintillator, which could allow high-precision neutrino detection on a new scale. So what is water-based liquid scintillator? It's a very simple idea. You take oil and water, and you mix them. Despite popular belief, it turns out that is possible. And the result is actually a target medium that gives you the benefits of both worlds. the benefits of a pure water detector and a large liquid scintillator detector. So you can build a very large detector because you have the low attenuation of water. It doesn't absorb very much light. You have directional information from the Cherenkov component in water, but you also have high light yield of scintillator, which allows you to go to very low energy thresholds. And the experiment that's being proposed is called Thea. It would be a 50 to 100 kiloton scale detector. This pale blue is an image of the detector, just to give you an idea of the size, roughly the size of the Statue of Liberty. And because of the high precision nature of this detector, you could achieve a very broad physics program, ranging from neutrinoless double beta decay through solar neutrinos, supernova neutrinos, and even long baseline physics, neutrino mass hierarchy and CP violation. So this is physics that spans 5 orders of magnitude in energy in a single detector. And I'm going to leave you with a bit of a brain teaser. In the same detector, you could show that neutrinos and antineutrinos are the same by observing neutrinoless double beta decay, and that neutrinos and antineutrinos behave differently by observing CP violation. So to conclude, neutrinos have led us on a very exciting chase. The recent decades have seen some major breakthroughs, but this is by no means the end of the road. These really just open the door to new and even bigger discoveries. And the next 5 years have the potential to change the way we think about neutrino physics and even perhaps turn our understanding of the universe on its head. Thank you.
I lied. There was no chance we were going to make up time. I do think it's time. Do we know if the coffee's been set up? I am going to assume it has. So the good news is hopefully our speakers are going to stay around for the coffee break and we can ask them questions then. But let's thank all 5 of our speakers again for this session. So.